Hello, and welcome to my video on volume of a solid revolution by washer method. So this is going to look a lot like what we did for disk method, but we're going to have what we call a washer or donut. So you can think about washer like a donut, where basically it's a circle with a circle cut out of it. So I'm going to show you kind of the progression of thought here. We have this bounded region between F and G, and we're going to be spinning this, for example, around, let's say, the x-axis, okay? So when I rotate this, you see how we have all this empty space right here? That's going to result in this hole in our cross-section. And when we look at 3 dimensions, we're going to have that same hole kind of cut out of the middle of this 3-dimensional object, okay? And when we've talked about all these previous questions, just like a disk, we calculate the area of a cross-section, figure out that function, and then we integrate that. Okay, and we know that, for example, in this case, if we have like a donut type shape or a washer type shape, we would basically do the area of the big circle minus the area of the small circle. So that would be pi, I'm going to use capital R, so pi r squared minus pi r squared, and we can factor out the pi's, so we get this calculation. Okay, that would be the area of all of this space right here. That's how I would calculate that. So this is our cross section. So area of our cross section. And as I've talked previously, if we just integrate that kind of function idea, then we're going to get our answer. Okay. So basically we have pi out front again, integral from a to b of big R of x minus little r of x, and each of these are squared individually, not together, okay, dx. And this is really difficult. This looks like a disk problem, but it's not. We have 2 separate circles, so we have 2 separate r squareds, okay? Now, let's talk about how r would be calculated in my example here. I'm going to kind of get this out of the way. Since we're spinning around the x-axis, okay, my inner circle is going to have this radius, which is basically from here to here. That would be little r. And then my outer circle would have this radius. That would be big R. Now that goes from your axis to your outer function, okay, or your top function in this case. So this is top and bottom, and then we have a new top and bottom for little r. Okay, so big R of x equals the outer or top, I'm going to say outer function, minus your axis, and little r of x is your, I'll call it inner function, minus your axis of revolution. So that's how we kind of figure out big R and little r. And I think this will make a little more sense, hopefully, once we do some examples. Now, when we're rotating around a vertical axis, I'm sure you probably can guess from our previous work how this is going to work out. Very similar, except everything is going to be with respect to y. So r of y, quantity squared, minus r of y, quantity squared dy. Again, the reason why we have 2 different r squareds is because we have to calculate the area of 2 separate circles and subtract them. And figuring out r is the hardest part of these problems. If you can get that part down, it makes these problems real straightforward, a lot like disk problems. Okay, so let's think about how this is going to work. So we're going to take this bounded region, and I already have a 3-dimensional object for you. Okay, we're going to spin it around the x-axis. So this is a horizontal axis. So this is horizontal. So we want to do everything with respect to x, which you'll notice we have these x values here and here. And we have our functions in terms of x. You know, y equals 2, y equals x squared plus 4. Okay, so we're going to spin that region around. And what's going to happen is we're going to get these cross sections that we've got like this big circle. I've got this huge circle and then like a little circle cut out of the inside. Okay, and we've got 2 radii. We've got one here. It's really hard to draw. We've got a radius right here, and then we've got a radius right here. We've got our big R and our little r. So we have to figure out what those are. Well, if we're spinning around the x-axis, okay, the way you calculate r is from your axis to your outermost function. That's going to be big R. And then little r is your axis to your innermost function. Now, one thing I probably should have clarified that's going to be very helpful, I think. How do we know if it's a disk versus a washer? Well, a disk has no, what I call empty space between our region and axis of revolution. So I'm going to call that AOR, axis of revolution. A washer has some empty space between your bounded region and your axis of revolution, AOR. So you'll notice in this problem, I knew it was a washer right away because if I'm spinning it around the x-axis, I've got this little sliver. It doesn't even matter how much it is. It could be the tiniest bit. But I've got this little sliver of space right here between my bounded region and my axis of revolution. So when that happens, it's going to create this empty space right here. Therefore, it's a washer problem because you are going to have to decipher which one is a disk, which one is a washer. Okay, so I've calculated or shown you now how to look at big R and little r. Again, you always go from your axis to your outer function, axis to inner function. That's big R, little r. So big R, think about it as now individually top minus bottom. So big R is going to be x squared plus 4 minus the y equals 0 because this is basically y equals 0. So that's just x squared plus 4. Little r, notice this function is always 2. So little r is 2 minus 0. Really, it's just 2. And we go ahead and plot this into our, punch this into our formula. We're going from 1 to 3. Big R squared, so x squared plus 4, minus little r squared. And these are both squared. And I'm not going to finish solving these problems completely. I'm just going to kind of get you going the right direction here. But we would FOIL this. So this would be x to the 4th. This is 1 to 3, sorry. X to the 4th plus 8x squared plus 16. And then you'd have a minus 4 from this. So that's going to give us a 12 dx. And then you would, as we've been doing for a while now, you'd find the antiderivative. Okay, and it would look something like this, 8/3 x cubed plus 12x. And you still got to plug in your 1 and your 3 and then simplify it. I'm going to leave it at that, though. Okay, we're really focused on the setup in these problems, I think, for the most part. Okay, number 6. We have these curves. All right, we're bounded by these. So we probably want to get ourselves a little sketch to see what's happening. So y equals x is this function right here. It's a line. And y equals 2 root x is going to look like this. Okay. And these are going to intersect at an x value of 4. Okay, so if I plug in 4, the y value is going to be 2. Again, if you're not sure of that, you would just set these equal. You would do like 2 root x equals x. So if you square everything, you're going to get 4x equals x squared. So 0 equals x squared minus 4x. So you would get x times x minus 4. Okay, and that would tell you the x values where these two functions intersect. So what we're doing is we're trying to take this region right here, and we're going to rotate it around the x-axis. Now, this is a washer problem because you'll notice that I have all this space right in here that's empty. It's not going to be filled in. Okay, so because we have that gap, if there's any kind of gap between our bounded region and our axis of revolution, in this case, the x-axis, then this is going to be a washer. This is a washer problem, okay? And we're revolving around a horizontal axis, so that means we're going to be doing stuff with respect to x, all things we got to consider. And then really, it's pretty straightforward to calculate your different r's. So if I started my axis of revolution, I go to the first boundary function that I hit. That's little r. If I go from my axis of revolution to my outer function, that's big R. Little radius, big radius. Then you're always going from your axis of revolution to the first boundary of your function, or the bottom function in this case, and then your axis of revolution to the second boundary of the function. So big R is going to equal, and you just think top minus bottom for each one. So top bottom. The top is 2 root x, the bottom is 0, so it's just going to be 2 root x. Little r, again, think top minus bottom. X minus 0, so this is going to be just x. And we know our formula, pi integral from a to b, so 0 to 4, because we're doing with respect to x, and big R squared, so that would be 2 root x squared minus little r squared dx. So we could clean this up a little bit. This is 0 to 4. We would get 4x minus x squared dx. And then you would go through, you know, find the antiderivative, apply the FTC, do all that fun stuff. So I'm not going to finish the problem again. I'm just going to go ahead and kind of get you going here. So 2x squared minus 1/3 x cubed. We would plug in then 0 and 4 and finish evaluating. Okay. Again, like I've mentioned a few times now, I'm just really focused on getting these things set up with you guys. All right. Now, what happens when we revolve around a horizontal line, but it's not the x-axis? So this is still going to be with respect to x because this is a horizontal axis of revolution. So you can kind of see the picture here. Obviously, you have a washer because as this shaded region sweeps around this axis, you're going to have all this empty space right here. So it's not going to be a disk. You'll notice we have a big circle and a little circle. Now, this problem is kind of giving it away, our calculation, but let's talk through how we find big R and little r. It's very similar every single time. If I start at my axis of revolution, okay, and I go to the bottom function, the inner function, the first function that I hit basically, that would be little r. If I start at my axis of revolution and I go to the outer function for the bounded region, that would be big R. And then we have to think about, okay, what is big R? Well, for this case, if I think top, bottom, okay, the top function is f of x. The bottom function is y equals -3. So minus -3, which equates to f of x plus 3. And we know this is f of x, right? So this is really x squared plus 5 because 3 plus 2 is 5. And little r would be very similar. Actually, shoot, you know what, guys? I apologize. I was looking at my functions wrong. This function up here is actually g, and this one is f. So this should say g of x. Okay, so this should be g of x. And in that case, if we're adding 3 to this function right here, I get 7 minus x squared. I apologize for the confusion on that. This function right here is actually g of x. Okay, so back to what I was saying. For little r, it's the same thing. This function here, if I think top minus bottom to find little r, in this case, this is f of x, this is -3. So f of x minus -3 is really f of x plus 3, and that would be x squared plus 5. Okay, the hardest part for these problems is figuring out big R and little r. So you have to really, really focus on how that calculation is done. And then the setup is always the same. We're going from -1 to 1. And we have big R squared, so 7 minus x squared squared minus little r squared. So that's x squared plus 5 squared dx. And you would have to, in this case, you know, FOIL both of these, combine like terms. So I'm just going to kind of get you to that point. I'm not going to even probably find the antiderivative because you guys can do that. You're really good with this stuff. So 49 minus 14x squared plus x to the 4th minus the quantity x to the 4th plus 10x squared plus 25 dx. And if we wanted to combine like terms, then I make sure I distribute the negative, right? That's why I had to make sure I kept those parentheses. So the x to the 4ths are going to cancel. 49 minus 25 is 24. And then I'm going to get -24x squared dx. And then you would finish the problem normally, but we're going to just leave it as this. So you really, 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 really have to focus on how to find the two different radii. And I think a lot of times the key is going to be drawing a good picture or having a good picture and knowing what to do. So we always start, again, just a little refresher, we always start our axis of revolution and you would go to the outer function that is creating your bounded region, the furthest function away. That would be big R. And then to make this calculation, you can just do what's the top minus the bottom. So g of x minus -3. Okay, and that should make sense because let me reiterate how this works, how functions work. I know it might seem silly, but this distance right here, okay, this distance from here to here, that's g of x, and this distance is 3. So if I did g of x minus -3, you'll notice we get g of x plus 3, which is what we want, because we're actually adding 3 to g of x every single time. Okay, that's actually what's going on here. But again, this calculation, we have to be able to figure out these things. That's really the newest part. The formula is the formula. You just plug stuff in. But calculating those is oftentimes difficult. Okay, let's do a problem where we're going to now rotate around the y-axis. Okay, so it's bounded by these 3 things. I already have a sketch for you. And it's rotating around the y-axis. So this means with respect to y, because we have a vertical axis of revolution. So we're going to be spinning it around that axis. Okay, so now we have to look at this kind of left to right. So if I start on my axis, I go to the outer function that creates my boundary. That's big R. Start on my axis, go to the inner function that creates my boundary. That's little r. And we can think just right minus left. Well, the right function here is x equals 3, and the left function is 0. So big R is 3 minus 0, which is just 3. You'll notice that this distance from here to here, here to here, here to here is always 3. That's why it doesn't have a function involved in it. Now, what about little r? Okay, think about it as right minus left. Well, the right function is y equals x squared, but we don't want it as y equals x squared. This is x equals plus or minus root y, and we want the positive case because it's the right half of the parabola. We've seen this problem many times. So r, little r, is right minus left. So root x minus 0, which is just really root x. So when you draw your r's, you always start at your axis of revolution, and you go to your outer boundary for your boundary region, and then your inner boundary. That's big R and little r. Okay. And now y values. Remember, we're doing this with respect to y. So we're going from 0 to 9. This is 9 right here, where they intersect. So we're going to go pi integral from 0 to 9, big R squared, so 3 squared, minus little r squared, root x squared. Sorry, it's supposed to say root y, not root x. I'm sure you guys caught that as you were watching. dy. Everything with respect to y, because we have a vertical axis of revolution. And this would be pi integral from 0 to 9 of 9 minus y dy. And this one's not terribly bad to do, right? This is just going to be 9y minus 1/2 y squared, 0 to 9. So if we plug everything in, we're going to get pi. This will be 81 minus 81 over 2 minus 0. Okay, so this is going to be pi times 81 over 2. And that would give us 81 pi over 2. Okay. And you can see the visual here of what would happen and why we have a washer problem. Because if I was to kind of think about the cross section here, I would have this circle, and then inside of it, we'd have like this kind of circular bowl cut out of it. So we're calculating really this area, and then the integral will give us the volume. Okay. I'm going to skip number 9, just to kind of save a little bit of time. We can always talk about that in class if need be. Let's look at number 10. Okay, this will be our last example. So in this case, we are going to rotate about this line, x equals -2. So this is going to be with respect to y, because this is a vertical axis. So right off the bat, I know this is y equals 9 minus x squared. I'm going to have to solve for x. So x equals, let's see, subtract 9, then divide by -1 and square root. So plus or minus square root of 9 minus y. Okay, and you'll notice we're using the right half because it says between 0 and 3, so we're using the right half, which means we just want the positive case, 9 minus y. So this function right here is actually x equals square root of 9 minus y. Okay, and we're spinning it around this axis right here, which is x equals -2. So for this calculation, and it's already drawn the picture, but we really should go through this. Okay, it is a washer problem again, because you've got all this space right here that's empty space. It's not hitting your axis of revolution, so we're going to have this kind of circular cutout, as you can see in the picture. And big R, again, start at your axis, go to the outer function. That's big R. Okay, so big R is going to be the right minus the left. So the right is root 9 minus y minus the left, which is -2. So this is going to be root 9 minus y plus 2. Little r, we're going from here to here, and that's little r. Now, little r is always 2, because this distance, I'm going from -2 to 0 every single time. But the calculation, you could think about it again, right minus left. This is x equals 0, so 0 minus -2, which is 2. So the volume, pi, integral from, we're going from 0 to 9 again. And we have big R squared, so root 9 minus y plus 2 squared minus little r squared. And that would be it. Okay. Again, I'm not going to finish this problem. I think this is sufficient, just kind of getting these things set up. All right, that's going to be it for this video. I know this one's a little long. I apologize. It's just this stuff is pretty hard. So hopefully these examples were good enough to kind of get you going. All right. Thank you for watching. If you have any questions, please let me know.